Okay, the last section of this chapter, we're going to talk about phase diagrams. So we've seen in this chapter that the phase of a substance depends on both its temperature, and particularly for the liquid and gas transition, it also depends strongly on the pressure. And so a phase diagram is a map of the phase of a substance as a function of the temperature and pressure. Alright, so this diagram is typical of what a phase diagram looks like. So in this case, we put the temperature on the x-axis, which is pretty typical. We've put the pressure on the y-axis. And then if we go to any pressure and temperature, it will tell us what phase exists at that pressure and temperature. And so we have these lines represent the boundaries between the phases. And so we have these three regions, and of course we have three phases: solid, liquid, and gas. So what I want you to do is, once I'm done talking here in a second, pause the video and make a prediction about which one of the regions represents the solid, the liquid, and the gas. So go ahead and pause it. I'll wait a second. Okay, you're back. Let's see if your predictions match what the actual regions are. And so we have the solid here, the liquid is here, and the gas is down there. And so it maybe makes sense that the solid has got to be one of these two, right? Because at the lowest temperature, that's where we should have the solid. And so the solid is either going to be here or here. But this is the solid region, because if we have a solid and we decrease the pressure enough, we can convert that solid into a gas. And same thing, if we have a liquid at a given temperature and we decrease the pressure, we can convert that liquid into a gas. Right? And with temperatures, right, let's say I started with a solid here. As I increase the temperature, once I get high enough, I'll melt it and convert it into a liquid. And then when I get even higher, I'll vaporize that and turn it into a gas. Now there are a couple interesting regions that I want to point out on the phase diagram. So the boundaries, right, this represents the solid-gas boundary. This represents the liquid-gas boundary, and this represents the solid-liquid boundary. And this point here where they all meet, it's a very special temperature. And pressure called the triple point. If we achieve this exact temperature and pressure, we can actually have all phases existing in equilibrium together. So that's kind of interesting. And then in the gas-liquid boundary, it actually stops at this point. This is called the critical point. And what's interesting about the critical point is once we exceed this temperature and pressure, we have what's called, so in this region, we have what's called a supercritical fluid. And it's sort of a new state of matter, or a different state of matter between a solid, liquid, and a gas that's sort of a hybrid between a liquid and a gas. And so it's sort of an unusual fourth state of matter when we get to temperatures and pressures beyond the critical point. All right, so I just talked about these on the last times, or on the last slide, but the triple point is the a unique temperature and pressure at which all three phases of matter can be in equilibrium with one another. And I've got another video that I didn't make, that someone else made, but I've got a link to it on the D2L site in my videos list, where a group has done an experiment where they've taken T-butanol to its triple point, and it's a cool video. And so you can see all three phases, the solid, liquid, and gas, present at the same time. So I definitely recommend take a look at that video. It's pretty cool. I mentioned the critical point. So once you're above the temperature and pressure of the critical point, the phase boundary between liquids and gases ceases to exist. And so supercritical fluids are interesting because they have properties of both liquids and gases. So while it has many of the properties of liquids, it can also dissolve things like a liquid can. It has many industrial applications. one that's kind of cool is one way to decaffeinate coffee beans is you take carbon dioxide and turn it into a supercritical fluid, and then it turns out that caffeine is soluble in the supercritical fluid, and it will remove the caffeine from the remainder of the coffee beans. So then you can grind up the coffee beans, make coffee, and you don't have any caffeine. I don't know why you'd want to do that. Coffee is gross to begin with, so the only reason to drink it is for the caffeine, but whatever floats your boat, I guess. Okay, so one thing I wanted to point out was specifically looking at the phase diagram for water. And specifically, I'm interested in the fusion curve, right? So the boundary between the solid phase and the liquid phase. And what you notice, and so this is a typical phase diagram that would apply for most substances. And if you notice, how does the slope of the fusion curve compare between most substances and water? And so hopefully you notice that the slope for the phase diagram of most common substances, the slope is positive, whereas the slope is negative in the case of water. And this has to do with the different densities of solid and liquid water versus most other substances. Right? So most substances become more dense when you go from a liquid to a solid, right? And so they'll actually contract in volume. And so for most substances, if you start with the liquid and you really greatly increase the pressure, you can actually convert that into a solid, right? You're forcing things so close together that it'll convert that liquid into a solid. But for water, it's the opposite, and it's due to the fact that unlike most substances, water is less dense in the solid form than the liquid form. And so if you take ice and you put a lot of pressure on it, you can actually convert that to liquid water without changing the temperature. And so that's sort of unusual. Most substances would be backwards. All right, so I want to finish up with just an example, kind of the way we might ask these questions about phase diagrams. And again, this is wrong chapter. We're still in chapter 10. But what I would like you to do is determine what phase of matter would exist for the following points on the phase diagram, in this case of carbon dioxide. Right, so if they gave me 20 degrees Celsius and 72.9 atmospheres, so I've got 72.9 atmospheres here, and so this would be 0 degrees, or not 0, but negative 273 degrees Celsius, right? And so as I go up and up and up and up and up and up, when I get to about 56.7, we're going to be at the phase boundary. So 20 degrees Celsius is going to be somewhere in here. And so at 20 degrees Celsius and 72.9 atmospheres, carbon dioxide would be a liquid. We know at atmospheric pressure, carbon dioxide would be a gas, but atmospheric pressure is about 1 atmosphere, so 72.9 atmospheres, right? We've got to increase the pressure quite a bit to get it to be a liquid at that temperature. Right? And then what phases would exist at negative 56.7 and 5.1 atmospheres? Well, 5.1 atmospheres and 56.7, that would put us right here. And so that's at the triple point. And so at the triple point, we have the solid and the liquid and the gas all present at the triple point. Okay, 1 atmosphere and 10 degrees Celsius. So I look at my chart. So here's 1 atmosphere. This would be negative 78.5. So 10 degrees is going to be somewhere in here. So clearly, point C would be a gas. All right, negative 78.5 in 1 atmosphere. So here, again, is 1 atmosphere and negative 78.5. So we're right on the boundary between a solid and a gas. And so that corresponds to the phase changes. So we would have both a solid and a gas present. And then finally, what would we have at 50 degrees Celsius and 80 atmospheres? So 80 atmospheres is going to be somewhere up here. 50 degrees Celsius is going to be above 31. So we're going to be somewhere in this region. So We're above the temperature and pressure of the critical point, so this would make a supercritical fluid.